Vertebrates are obviously segmented animals. One can observe this in the repeating vertebrae, ribs, nerves, the repeating bands of muscle such as intercostal muscles, or even the segments of the rectus abdominis in humans. But when one observes embryos, it is even more evident in the repeating blocks of tissue known as somites. Vertebrates share this feature. There is even segmentation of the hindbrain seen here, which disappears in later development. Chordates apparently began as segmented animals, as evident in the segmentation of Amphioxus, a cephalochordate. There are obviously other segmented animals as well. The annelids are known as the segmented worms. One can observe segments in earthworms and leeches. Arthropods are well known for their segments. One can observe this in centipedes, millipedes, but then even in abdominal segments and other segments which fuse in arthropods. There is even segmentation known in early mollusks, both in fossil forms and in the most primitive mollusks alive today, the chitons. These are segmented mollusks. Where did segmentation come from? In the coelomate model of Bilaterians, the earliest coelomates were segmented, and thus this explains the segmentation which occurs in most coelomate animals. This segmentation evolved once. However, once Bilaterians were reclassified, thus the segmented Bilaterians are now classified as cousins of many unsegmented groups. So annelids, which are segmented, are closely related to flatworms, which are unsegmented. Arthropods, which are segmented, are closely related to nematodes, which are unsegmented. And thus, especially in the Lophotrochozoans, where there are many phyla which are unsegmented, the origin of segmentation is unknown. However, it now seems that the segments of many of these groups shares some molecular basis. So, for example, we know that Drosophila, an arthropod, and in vertebrates and lancelets, there are homologs which are shared in segmentation, such as the gene engrailed and the gene hairy. In spiders, the genes notch and delta are used in segmentation, just as they are in vertebrates. In an annelid, genes like engrailed, wingless, and ladybird are used in segmentation as they are in arthropods. And thus, if annelids and arthropods use some of the same genes in segmentation, this suggests that the earliest protostomes, the ancestors of all of the ecdysozoans and Lophotrochozoans, was segmented. If some of these invertebrates share genes involved in segmentation with vertebrates, this then implies that the ancestor of all Bilaterians was then segmented. Now, this is difficult because Bilaterians include so many unsegmented groups. Did these other groups lose their segmentation? Also, this pushes the ancestry of segmentation far back in the family tree. Was the ancestor of nematodes, which can be simple and microscopic, and flatworms, which are very simple acoelomate worms, was their ancestor a complex segmented worm like perhaps an annelid worm? And so thus the pattern of segmentation in the Bilaterian family tree, which seems to result from a common ancestor given genetic shared mechanisms of segmentation, is a bit confusing given the reclassification of the Bilaterians.